Finish up the last little bit. We're done with chapter 4, but we have a few more slides. We're gonna go through those. Then we're gonna go backwards, I think, to chapter 3 today. So really last time we got into hybridization. And again, hybridization is really sort of the another sort of bonding theory that helps explain certain things like bond angles that we see in certain molecules. And it is based on really taking atomic orbitals like S's, P's, and D's and sort of combining them together to make these hybrid orbitals. And there really is a few different types of hybrid orbitals. There's sp, there's sp2, there's sp3, there's sp3d, there's sp3d2 or squared. And each of these really do sort of correlate to the electron pair geometry that we talked about. And really kind of the simplest way to sort of remember sort of the geometry that goes with the bond angle and all that is just really just to count the letters. So sp is 2 letters. It's kind of like 2 electron pairs, which kind of goes with the linear geometry. sp2 is 3 sort of letters, which is like 3 electron pairs, which goes with the trigonal planar, 120 degrees. sp3 is 4 electron pairs, which kind of go 4 letters, which is kind of like 4 electron pairs, goes with tetrahedral. And then when we get into our sp3d, sp3d2, we do get into sort of the expanded octet. So there's kind of like 5 letters there, which goes with our triangular bipyramidal. And obviously this guy here has 6 letters, which goes really kind of with our octahedral sort of geometry. And again, they sort of correlate to those electron pair geometry, not necessarily the molecular geometry, but that electron pair geometry is where we sort of apply this hybridization. Really, the easiest way to quickly assign hybridization is to, frankly, just mark it off. So just remembering from electron configuration, how many orbitals each of those things have, the S, the P, the D. You want to count electron pairs around whatever atom that you're going to try to apply hybridization to. A lot of times that is the central atom. You can apply hybridization to outside atoms as well. Again, typically, usually hydrogen is the only one that does not get any type of hybridization applied to it, as it only has 1 electron. So basically you count up the electron pairs just like you would be doing molecular geometry or geometry, and that means basically any double bonds or triple bonds count as 1. And also the other thing, as I mentioned, that a lot of times people will sort of overlook when they're doing hybridization is the non-bonding electrons. So it doesn't really matter if they're dots around that atom or if they're lines, bonding or non-bonding electrons, you do count them all. And again, however many you have, basically you always start with S, work your way to the P, and just kind of mark off the boxes. And then that will pretty much give you your hybridization that you should have for that. And that's pretty much a foolproof way that you can sort of assign hybridization and usually get it fairly correct. We sort of finished up last time talking about molecular polarity. And remember, molecular polarity is really the entire molecule as a whole, taking into account all the bonds that are there and whether or not as a whole that molecule is polar or non-polar. Is there a positive side or a negative side to that sort of molecule? Again, the only place really where bond polarity, and when we talk about bond polarity, that is typically where we use the difference in electronegativity values to figure that out. And bond polarity is really just between these 2 atoms. You know, would we expect those electrons to be shared equally or unequally? It doesn't necessarily mean that the entire molecule will be polar or non-polar, but bond polarity is what we use for that. We do use still that same sort of arrow that points to the more negative side, this side, the more positive side of that particular bond. And the only place, as I was mentioning, that sort of bond polarity and molecular polarity sort of crossover is when you have diatomic molecules. And that's really because in diatomic molecules, there's only one bond. So it makes it pretty simple. Because there's only one bond, either that bond's going to be polar or non-polar, and that would make the molecule either polar or non-polar because there's no other bonds in that particular thing. It does get a little bit different when you're dealing with 3 or more atoms involved. When you're dealing with 3 or more atoms involved, you do have to look at whether or not, there are polar bonds, and that you would use bond polarity and the difference in electronegativity values, or even just a generic sort of trend of electronegativity off the periodic table to determine that. And the second thing is, obviously, if it does not have polar bonds, it most likely is going to be a non-polar molecule. If it does have polar bonds, then the second thing that you do need to look at is the molecular geometry. So not the electron pair geometry, but the molecular geometry or the shape of it, and to help you determine whether or not the molecule is going to be polar or non-polar. So there is sort of multiple ways that you can kind of do that. You can do it the traditional way, which is looking at the bond dipoles and those bond dipole arrows, which are vectors, which has direction and magnitude, and see if they add to each other or sort of cancel from one another. But most people, probably the easier approach is to think about it in terms of sort of symmetrical geometries and unsymmetrical geometries. And really, because those bond dipoles are vectors, they can cancel each other out, but they could also sort of add to one another. And typically, when we have symmetrical geometries, those are guys, when you draw the Lewis structure, pretty much there are no dots on the central atom. So in most cases, there's no dots on the central atom, no lone pairs. And if everything on the outside is the same, then it will most likely be a non-polar molecule. It's almost a pretty safe bet that that's going to be the case. The opposite of that as well, though, is if you happen to have no dots on the central atom and everybody on the outside is not the same elements, then most likely it will go from non-polar to polar in those situations. I would say in pretty much a good majority of the time that's the case. We do have some unsymmetrical geometries, and really the way you can recognize that is when you do draw your Lewis structure, you have some dots on the central atom, and that means it has some non-bonding electrons. And usually that would give rise to some unsymmetrical molecular geometry where all the atoms and those bond dipoles are going to end up in sort of not equal from each other locations. And that usually will result in those guys sort of adding to each other. And typically you'll get a polar molecule that usually will occur in that particular case. There are a couple of things or exceptions that you should think about when you're doing it. We talked about the linear, which is 2 electron pairs and 2 bonds. Because that is a straight line, they could go opposites of each other and cancel each other out like we see in CO2. They could head right at each other, which would also cancel them out. But remember that they could potentially end up heading in the same direction, which means that it would be polar in that case. And then there's kind of 2 exceptions to the quick dots or no dots sort of rule. And that is if you have either the linear, that's the expanded octet, which is 5 electron pairs and 2 bonds, or you have the square planar, which is 6 electron pairs and 4 bonds. Those guys will have dots on the central atom. But again, if everything on the outside is the same, because they actually are going to be symmetrical, they will actually end up being non-polar. So in most cases, so that's kind of the 2 exceptions for dots or no dots, is those guys could have dots and they would still be non-polar. Any questions on any of that stuff that we talked about there? Okay, I think we just had a few more slides, so let's go through some of these here. So as we talked about polarity of a molecule, in order for a molecule to be polar, again, it does need to have polar bonds and those unsymmetrical shapes. A reminder that if something is polar or is a polar molecule, it will have what is referred to as a dipole moment. And so, for example, if we took something like water, again, it has individual bond dipoles heading towards the oxygen as it is more electronegative. As we talked about, they will add together and create an overall dipole moment for this molecule heading in this direction. The dipole moment is also really the same arrow that we use for those bond dipoles. And it means the same thing. It means really in this water molecule, the hydrogen side is going to be more positive because the electrons are kind of heading towards the oxygen side in this molecule, which means the oxygen side would be more negative heading that way. So overall distribution of electrons in the entire molecule is unequal, and it creates a positive side of that molecule and a negative side of that molecule. And dipole moments can be sort of different sizes, if you will. So there can be, a very small sort of dipole moment, and there could be, a pretty big sort of dipole moment in terms of the separation that can affect. The importance of sort of polarity of molecules overall, as we'll talk about also in a later chapter, is it really is how different molecules or even the same molecules are able to interact with one another. And that is what the intermolecular forces are. Intermolecular forces are basically how one molecule interacts with another. And again, it could be another molecule of itself. It could be a different molecule altogether, but it's basically how these guys come together and sort of interact. And the basis of pretty much all intermolecular forces is a simple interaction of positive and negative attractions to one another. So basically all intermolecular forces are that positive and negative attraction. So the positive side of one molecule is attracted to the negative side of another molecule. And that is basically how all of them work together. So for example, if we do have a polar molecule, that means that one side is going to be more positive, one side is going to be more negative. And if you put that together with another polar molecule, one side is going to be positive, one side is going to be negative. And again, the opposite sort of sides, the positive side of one and the negative side of another polar molecule, allows them to basically interact with one another. This type of interaction, as we'll talk about later on, is what is sometimes referred to as a dipole-dipole interaction. And that is typically what polar molecules use a lot of times to interact with one another. They're able to do that because they have a fixed dipole moment, which means they always have that. They always have a positive side. They always have a negative side. They're good to go when they come near each other to interact with one another. They don't have to wait for something to happen. And that's different than what we actually see when we get something that is nonpolar. Nonpolar are pretty much neutral. They have no side that's more positive. They have no side that's more negative. They have to rely upon, as we'll talk about in more detail a little bit later on, what is sometimes referred to as dispersion forces, which means they have to have something occur for them to sort of gain a charge so they could kind of interact with it. It could be like the electrons moving from one side to the next. It could be they come up upon something that's positive or negative, like an ion or a polar molecule. But they need something like the electrons, for example, in this guy, to all decide, I'm going to go that way. And what happens is temporarily what will happen is it will now have a positive and negative side just because electrons decide to go kind of one way versus the other. And if it's still next to this nonpolar guy over here, the electrons in this guy will decide, I don't want to be near that negative side, right? Because opposites don't like to be near each other. And this guy will then kind of create a temporary charge. And now from the sort of temporary charges, that's really how nonpolar guys sort of come together. They have to have something occur for them to gain those charges to allow them to interact with one another. As soon as those electrons kind of go back, it's going to break apart. It's going to kind of fall apart. And same thing with if it gets near something that has a charge, it will kind of temporarily gain that charge, but will sort of fall apart as well. And they use what is referred to, as I mentioned, dispersion forces, which is a relatively weak sort of interaction. So really what makes sort of molecules sort of interact well with other molecules is if they are using the same type of intermolecular force, which is really based on the polarity of those molecules. They're going to really be soluble in each other. They're going to mix really well. They're going to interact really well with one another. But if they're using something that's really sort of different from one another in terms of their intermolecular forces, they're going to have a very hard time interacting with each other and maintaining that sort of interaction with one another. Any questions on that there? And that does affect things like boiling points and melting points. So things that have a really strong sort of intermolecular force will hold themselves together a lot tighter, which require a lot more energy to break them apart, like is what happens at a boiling point, right? You got to break everybody apart into the gas phase. So if they're held together by a really strong force, which is like a dipole type force, it's going to have a much higher boiling point than something, say, that's organic, which uses like dispersion forces, those non-polar type of things. It doesn't take a lot of convincing to get them into the gas phase. And it has a much lower boiling point and melting point. So here's just some examples. Our net dipole moment, say in something like HCl, we know that, again, that is a polar bond. And because it's diatomic, that molecule would be polar. Again, the dipole moment would be heading towards the chlorine. We talked about CO2, I think, the other day as well, and it's also a very good example of the idea that you can definitely have polar bonds within a molecule, but because of the geometry, they may cancel each other out, and it actually will be a non-polar molecule. So that's something to keep in mind. Sometimes people feel like, oh, it's got a polar bond, it's going to always be polar, and it has to look at that geometry, especially with 3 or more things that are involved. And there's our water with our dipole moment happening. Again, this is sort of a diagram of where the electrons are. Red is kind of hot, so a lot of electrons in that area, kind of the bluest side, not so much electrons happening in that area there. And again, that means that the water is more negative than the hydrogen in that case. This is NH3, and again, if we drew NH3's Lewis structure, looks like this. And again, we could do our quick, I see dots, I see everything on the outside is the same. So it's going to be polar. And in this case, we have a dipole moment heading this way, where again, here, the hydrogen going to be more positive in that molecule. The nitrogen here is actually going to be more negative, as nitrogen is a little bit more electronegative in that particular case. As I was mentioning before, there's this idea when we talk about sort of how things interact based on their polarity. Like dissolves like, so things that are polar work really well with things that are polar. Things that are non-polar work really well with things that are non-polar because they're using the same intermolecular forces. It's really only when you cross over between polar and non-polar that you do run into some trouble. Again, they don't really have the same sort of working interaction that they do with that. And that's what happens, for example, when we take something like water and oil. Oil is pretty much all carbons and hydrogens, long chains of carbons and hydrogens and carbons attached to carbons, which are pretty much all non-polar. So oil is pretty much a big non-polar molecule. Here we have water on the bottom, which is definitely polar. And as you know, what happens when you put water and oil together, or if you don't know, that is what happens. It separates out. Oil usually ends up on top. Now, because everything technically can do a little bit of dispersion forces, which is what nonpolar molecules do, you can sometimes see some mixing occur for a little bit, right? Kind of like oil and vinegar salad dressing, right? You can mix it up, right? It mixes for a bit, but if you let it sit there, it's eventually going to sort of separate themselves out. And the same thing happens here. Overall, although they can interact for a short period of time, they cannot maintain that interaction. And that's why eventually you see, things to separate out from one another. And again, usually the oil is on the top layer there, that non-polar, and our polar guys on the bottom. That's actually what we saw as well when we did that experiment with the hexane, which is non-polar, right? And then the aqueous guys, which were really polar or water. We had the water layer on the bottom, that aqueous layer up on top. I'm sorry, that non-polar layer up on top of hexane. And that's where we found our non-polar molecules like Cl2, right? Br2. I think we had I2 there as well. Those are all non-polar molecules. And that's why we knew that they would be up in the top layer, because that's non-polar, so they interact really well. And those guys would not want to be in the bottom layer. When things become ions, like sodium ions, chloride ions, those are aqueous things, and those are water-based sort of environments. And that's why they end up in the bottom layer in that sort of experiment. That is basically soap. And in case you're not sure how soap works, soap actually has 2 parts. Soap actually has a non-polar part. Actually, I went too far with my circle there. Back here, non-polar part, which is all the carbons. And up here where this C double bond O minus, this part here is actually polar. sometimes referred to as the nonpolar tail of soap, and a polar head of soap. And soap works really well because most dirt is nonpolar. So the nonpolar part there of soap basically attacks and attaches to the dirt and creates what's sometimes referred to as a micelle. It kind of traps all the dirt together because nonpolar part is going to work really well. What it also does, it aligns itself out with the polar part of soap on the outside, which is that part all the way around. And that's really good because usually when we use soap, the last thing we do is wash it off with water, right? So the outside is very soluble in water. The inside, where the nonpolar part of soap is, traps all your dirt. So when you wash it with water, out goes everybody, dirt and all, you're clean. It's a good thing to know how soap works, I suppose. Yeah, any questions on that there? So as you can see in that, and it happens in a lot of organic molecules as well. There are molecules that have like a polar part and a nonpolar part, and it does affect some of their sort of properties depending on sort of what parts are there. So for example, when you go to organic and you talk about alcohols, they have an OH group, which is very polar, like what you see in water, which makes a lot of alcohols, very small alcohols, to be very soluble in water. But there is a limit to it. When you build up a lot of, say, the nonpolar part in those molecules, the solubility starts to drop a lot because it just gets too big to interact well with water. Any questions on that there? All right, so take a moment here for each of these, decide whether or not these molecules are polar or non-polar. So take a moment and see what you end up with here. Okay, let's take a look. So we do have some electronegativity values, so we'll use it. But we do have both things here that are 3 or more atoms. So we really do need to look at, are there polar bonds? And we do need to look at the molecular geometry of it as well. So we'll use it for help here. Again, we don't really need it because it's nitrogen and oxygen. So we should know that it is going to be a polar bond between those two. Again, we can see nitrogen is 3, oxygen is 3.5. So when you take the difference of that, in electronegativity values, you got 3.5 minus 3 gets you 0.5, which is a polar bond. It would head towards the oxygen in this case, right, as it is more electronegative. Now, in this case, when we look at nitrogen and chlorine, even from the periodic table, you could get a pretty good idea that it's going to be nonpolar because nitrogen is further up. Chlorine is diagonal a bit, but not directly diagonal. So it's one of those ones down and over where they sort of cancel each other out. And that's what we see here. They both have an electronegativity value of 3, which means this bond here is actually going to be nonpolar, right? As you do the 3 minus 3 gives you 0 type of deal. So it does have polar bonds. We want to look at the geometry here. Geometry here is 3 electron pairs around the nitrogen. Again, 1, 2, and 3, and 2 bonds, which means that is angular. Right? So that is one of those unsymmetrical geometries, and we do have dots. And basically, if we redraw this, it's kind of doing this thing. And basically, we have this polar bond, nothing happening on the other side. So you could think about if you just pulled from that side, right, the whole thing is going to move, and it would be a polar molecule in this case, right? Any questions on that there? Over here, we have sulfur and oxygen, and sulfur there being 2.5, oxygen being 3.5. Once again, you actually don't need the numbers either because they're in the same group on the periodic table. Oxygen is further up, which means it should be more electronegative and should create a polar bond. And we would have 3 polar bonds in this case. So we definitely do have 3 polar bonds from the difference in electronegativity. 3.5 minus 2.5 gives us 1 for the sulfur oxygen bond. In this case, in terms of geometry, it's got, in terms of electron pairs, it has 3, 1, 2, and 3. And in terms of bonds, it also has 3, which means it is trigonal planar in terms of its molecular geometry. And that is a symmetrical geometry. You know that also from just looking at fluid structure. I don't see dots, and I see everybody on the outside is the same. So I know that this is going to be non-polar. And that is because really that geometry is a triangle, right? right? And basically those guys, there are bonds are at each of these corners. So it's like all three of these guys pulling on the rope equally, right? Nobody's going anywhere, right? They're going to cancel each other out in that case, and it would be a nonpolar. So really quickly, even using our quick approach, I see dots on the first one, probably going to be polar. I see no dots on the second one, going to be nonpolar. So that's a good way to kind of do it really quickly. Any questions on molecular polarity or any of those type of things? Okay, so that should officially kind of wrap up this chapter. We did our CO2 a couple times already, so we won't look at it again, but obviously here, this is the correct geometry, which means this is why it's nonpolar. This is the incorrect geometry. So again, you do have to look at that geometry. All right, we're going to roll back to chapter 3 here in just a second. And we're going to talk about nomenclature. So we're going back to chapter 3, which should be the last part of chapter 3, and we're going to talk about nomenclature. So we're going to talk about how to name everything, and hopefully everybody will remember all this, and we'll talk about it here. So really in nomenclature, as we just finished up talking about bonding, there's really kind of two types of bonds, or really two types of compounds, if you want to think about it. There's ionic compounds, which always contain a metal and a non-metal, as we talked about. And as we talked about, always in this situation, we're going to get that electrons to be transferred. And the result of that is really important as well in terms of naming and nomenclature. We will end up with our metal becoming the cation, which is positively charged, our non-metal becoming the anion, which is negatively charged. And as we talked about, there's no sharing of electrons between those. It is the electrostatic attraction between the positive side of the cation and the negative charge there on the anion that holds that together. And that is different in terms of nomenclature than how we deal with what is sometimes referred to as covalent molecules or molecular molecules. And those are between two nonmetals. And as we talked about, obviously, because they're nonmetals and they have very similar periodic trends, they're going to do some type of sharing of electrons, right? And as we talked about during the bonding there, the sharing of electrons definitely could be equal sharing of electrons, which results in maybe a nonpolar molecule. Could be unequal sharing of electrons, which results in a polar molecule. But there's some aspect of sharing. And really, when we talk about naming, we do kind of break things up based on these kind of two interactions, whether or not it's more ionic or if it is more covalent or molecular and sharing of electrons that basically occur. So to do this, obviously, that's a periodic table. Looks good. That's still a periodic table. But obviously, as we talked about, I think maybe when we were talking about electron configuration and stuff like that, there are certain elements that have sort of fixed charges when you look on the periodic table. Also a reminder that things on the periodic table, when they are by themselves and not attached to anything else or combination with anything else, they have no charge. So it's really only when they kind of go the ionic route there and a metal and a non-metal get together that they do gain a charge. Other than that, they really don't have charges. But when things do make a charge, there are certain fixed charges, and everybody in group 1 will make a +1 charge. Everybody in group 2 here, when they do make a charge, will be +2. We do skip the middle, which is our transition metals, and group 3, for the most part, I would say probably aluminum is the one that you'll see the most, which is +3. Boron is more so treated like a non-metal and doesn't really kind of make a charge. And sometimes people will include gallium underneath it as well as +3, but most of the time it's aluminum right there that you're probably going to be dealing with. We then sort of skip group 4 and we go to group 5, and that's going to be -3. And those are the non-metals here we're talking about. So above the staircase, the non-metals. Group 6 will make a -2, and group 7 will make a -1 charge. And again, there we're talking about the non-metals above the staircase. in some of those groups below the staircase, they're metals, right? So above the staircase being our non-metals. And that makes sense based on what we've been talking about. Obviously, our metals there are positively charged, right? Our non-metals guys negatively charged because they're gaining electrons and things like that. The transition metal region typically will have a variable type charge, but there are three sort of exceptions to that are transition metals that when they do make a charge, they pretty much have a fixed charge. And that is zinc and cadmium, which is right here. These guys will make a +2 charge. And if you hang a left there at cadmium to silver, silver will make a +1 charge. Yeah. So those three are sort of exceptions in the transition metal region. They have fixed charges, and those will always be sort of their charges. Pretty much everybody outside of that in the transition metal region, all these guys here, through here, and even sort of outside the transition metal region, but below the staircase where we have things like I'm not sure what I circled there, but lead and tin and those guys, bismuth, they have the ability to make a variable type of charge. So although they're not technically transition metals, they also, in terms of sort of nomenclature, are sort of grouped in with transition metals as they have the ability to make a variable type charge. Tin, lead, you come across a lot as you go through it. So that's obviously really important to know those charges. It will make it much, much easier, obviously, when you go to name things. All right, so let's talk about a couple things here then first. Let's start with our ions. So when we have ions, obviously, we do have things that are charged. And we have cations, which are positively charged, and really they do come from metals. And the way that we name a cation, if we have just a cation by itself, not really attached to anything else, and is positively charged, we pretty much just use the name of the metal or the name of the element, and we kind of put ion at the end of it. So if we had H+, that would be the hydrogen ion. If we had Na+, that would be the sodium ion. We had Ca+2, that would be our calcium ion. And so forth. So any type of positive ion, we basically just use the name of the element, and we basically put ion after it. Now, if we have our anions, which are negatively charged, and usually are non-metals. Let's see, this guy here is usually our metals. We actually do end it with IDE at the end. So we do kind of drop the last part of the name there and put IDE at the end. So hydrogen is one of the few elements or only elements that can kind of go both ways. It could be positive in certain cases. It can be negative in certain cases. And we would do the same thing. This would be known as the hydride ion. We have oxygen with a -2 charge. We drop the last parts of oxygen. This becomes the oxide ion. We had Br-. This would be the bromide ion. So IDE. So we do, again, typically drop the last part there and put our IDE for our negatively charged guys. Again, our positive charged guys, we just basically use our name and the ion. Couple of things about ions is if you are writing an ion, it should have a charge. Yes, if it is an ion, so it should not just be the symbol. You should have the charge written with it. And again, if you're going to name it, you should put ion at the end of the sort of the name there for those two things. When we do take anything that is positively charged cation and a negatively charged anion, when we put them together to make the formula, We want the overall charge to be 0 in the formula. So for example, again, if we took something like calcium, which is +2, and we put it together with Br minus, in this case, if we just put it straight up together, we would end up with CaBr plus, right? The charges would not cancel out. We actually need 2 of the minuses here. -1 - 1 is -2. That balances out the +2. And the correct formula would be CaBr2. The purpose of that, as we talked about, actually goes back to bonding of what we were talking about. And the purpose of making sure that it does equal 0 in the simplest way possible is it allows all of those elements to reach the noble gas configuration in terms of electrons, which is really the purpose of the bonding. So that's really why we do balance it out to 0. If we didn't balance it out to 0, for example, in this particular case, like we kind of talked about when we looked at our Lewis structures, our Lewis dot symbols, we were doing bromine. We would only allow, in this case, calcium to transfer 1 electron. It would still have 1 and actually would only become +1. And this guy would become -1 in that particular case. And it's not going to be happy in that situation because really there's still an extra electron, right? He would only back up to where are we out there? Potassium, which is definitely not a noble gas. So again, to do that, like we talked about, it needs that extra bromine basically to get rid of that so it can become fully +2 and get back to that noble gas configuration. So it's really important to balance out the charge to 0. It allows it to get to those noble gas configurations like we talked about when we talked about ionic bonding. Also, when we are dealing with anything that is ionic, it is always the cation first, positive guy, followed by the anion. So it is always that way when you do both the formula and you do the name. So it's always positive guy first, followed by negative guy when you do both of those things. So that is why in this case we wrote CaBr2 and not Br2Ca. Yes. Plus it looks weird. Yeah, so don't do it that way. So it's always metal, non-metal, positive, negative guy, both in formula and also in name. Any questions on that there? All right. So here's a table, and you have a similar table in your book. Again, you can see what we talked about. Again, our hydrogen being really the only one that could kind of go both sides. A case where hydrogen would be negative is when it comes after a metal. So that's typically where hydrogen will become negatively charged because the metal obviously will be positively charged. So the hydrogen will be negative. Other than that, you pretty much could assume probably hydrogen is +1. But if it does come sort of behind a metal in a formula, it's going to be really the negative version of it. All right, so let's talk about ionic compounds. And sometimes ionic compounds are broken up into sort of type 1 or type 2. And the first one we're going to talk about is type 1 ionic compounds. It contains a metal and a non-metal, which means it is definitely ionic, as we can see here. And again, in this situation, our metal is going to send that electrons over, and that will create our positive cation from the metal and our negative anion from the non-metal. Pretty much the deal with naming is this: if you have a metal involved in the process, it is the most important thing. So really everything else doesn't matter. It's really always the metal that's most important in terms of when you are naming. So when you have this situation of a metal and a non-metal in a type 1 situation, it is the metal that's most important. The metal will come from group 1, 2, 3 on the periodic table. It may be zinc, silver, or cadmium. And basically what all of these guys have in common is they all have fixed positive charges. So these are the guys that have the fixed positive charges. So if you have something like sodium, which is group 1, will always be +1. You'll never find sodium as a +2, +3, or anything like that. It has a fixed charge. Doesn't matter who it's hooked up to, doesn't matter how many it's hooked up to, it is always going to be that charge. So these guys that have the fixed charges, which is basically group 1, 2, 3, and again, those 3 from the transition metal regions, the zinc, cadmium, and silver, they always have these fixed charges. The nice thing about that is once you can sort of identify this as a type 1 compound, that is a metal and a non-metal, that's pretty much all you have to worry about. And you could go really right into the naming part of it. And the naming part, when you do identify it as that, is you use the whole name of the metal, or the cation, and the non-metal pretty much gets the IDE treatment at the end. So basically, whole name of the metal, IDE for our non-metal. So that is how we get to something like NaCl. When we look at this, Na is sodium, which is a metal. Cl is chlorine, which is a non-metal. So that right off the bat tells you it's ionic. And because it's ionic, it is the sodium that is most important. And we see that sodium is group 1, which means it's a type 1 compound. And now all we have to do is name it, which would be sodium chloride. Now, if we had something like our CaBr2 that we saw earlier, this is calcium, which is a metal. That is bromine, which is a non-metal. So automatically that tells you it's ionic. No sharing of electrons happening here. We would focus our attention on the metal, or the first guy. And calcium is group number 2, which tells you it's a type 1 compound because it has a positive fixed charge. We go right into our naming. This would be calcium, which is the whole name of our metal. And the bromine gets the bromide IDE at the end of it. It is calcium bromide. It is not calcium dibromide. Yes, there is no prefix here. It doesn't matter if you got 400 of those. It is just bromide. Yeah, it has no effect in type 1 naming. You should not, I'll say it one more time, should not use the prefix ever in a type 1 ionic compound. There is a place for prefixes, and we'll talk about it. This is not the place for it. So some people like to put it in because it makes it look more chemistry-ish, almost sciencey, but don't do it. You don't want the X. Again, we talked about a second ago why there is 2 there, right? And there's 2 because it allows everybody to get to that noble gas configuration. It allows the overall charge really to be 0, which is the result of that, but it has no effect on the naming. Also, if you had 2 or more of the first guy, the metal, it has no effect on that name either. So you would just call it by the metal name. So it doesn't matter how many of those guys you have in a type 1 situation, you just use the whole name of the metal and IDE there on the non-metal. Any questions on that there? All right. So here's a table there of some of those charges we were just talking about. And again, obviously our zinc, cadmium, and silver do fall upon that. Now, one thing that I will say here is our friend hydrogen, which is here. And hydrogen, right, is a non-metal. And it is over there on top of group 1. And a reminder, not part of group 1, but it is a non-metal. Although it really is a covalent type of compound where it is sharing electrons because it's a non-metal with another non-metal. When you do have hydrogen involved, it's the only non-metal where we really do sort of treat it more like a type 1 compound, even though technically it's sharing electrons. It is named like a type 1 compound. So we don't really follow the non-metal naming for it. And that means that if you did have something like HCl, I guess I have to draw it right like that, or HCl, that's a gas, for example. We think of this really as like H plus and Cl minus, and we think of it as barely, we just call it hydrogen chloride. And even if you do have more than one hydrogen, like maybe you have something like H2S, sulfur is group 6, which means it has a -2 charge. Hydrogen obviously has a +1 charge. So in this case, we need 2 hydrogens to balance out the -2 charge that we see on the sulfur. We would still call this hydrogen sulfide gas, which you don't want to see. Yeah, sulfide gas. They took it out of Chem 200B. You don't smell it anymore, so that's good. But hydrogen sulfide gas would be how we would name it, even if you had more than one hydrogen. So hydrogen is a little bit of exception, and also sort of, like I said, it's thought more of being ionic, even though technically it is sharing electrons in terms of how it's named. And that's really because in most of these cases, we see these guys a lot of times in an aqueous environment, which makes them acids. So they actually do become ionized in that sort of environment. So a lot of times that's why we sort of name it like an ion, even though technically speaking in the gas form, everybody's sort of sharing electrons and stuff like that. All right, so why don't we try some here? Why don't you give the names of these guys? Maybe we'll switch this one out since I apparently did that one a little bit early. So we'll do, let's do BA. Do that one. And then why don't you also give the formulas here for some of these guys here? Let's do sodium oxide. Let's do silver nitride. Let's do magnesium. All right, so names on the left there, correct formulas on the right. A, which is potassium, we have Cl, which is chlorine. So right off the bat, that's a metal and non-metal, so that should tell you it's ionic. Also should tell you should look at the metal, and potassium is group number 1, which means it has a fixed charge, which means it tells you it's a type 1 compound. So really all you have to do is get to the naming part. So K is potassium. And Cl becomes chloride as we drop the last part of chlorine in this case. The cation here, if you were asked what is the cation, it is K+, has a charge. The anion here is Cl-, also has a charge as well. Looking at the next one, we see Zn, which is zinc, which is a metal. S, which is sulfur, which is a non-metal, so it tells you it's ionic. Looking at zinc, zinc is a transition metal, but it is one of those 3s that does have a fixed charge, so it is part of type 1, and that means we could go right into the name of this being zinc sulfide, as sulfur gets dropped the last part there and the IDE gets put in there. The cation in this case being zinc that has a +2 charge. The anion in this case being sulfide, which has a -2 charge. So that's again why you just need one of each of those guys to put it together to equal 0. Coming down here, we see Ba, which is a metal. We see P, which is a non-metal, phosphorus. So it's ionic. And again here, barium is the most important thing, which is group 2, has a fixed +2 charge. That means that this would be barium and phosphorus gets the IDE treatment at the end of it. So that is barium phosphide. Again, no prefixes here because of the numbers. The numbers are there because, again, barium, which is the cation, is +2. And the anion in this case is phosphorus, which is -3. Common number between 3 and 2 is 6, right? So you got to get each of those to 6. That is why there's 3 bariums. Number goes to the guy to the left, right? So 3 times 2 is +6. There's 2 phosphorus. The 2 goes to the phosphorus to the left there. 2 times 3 is -6. So +6 -6 gives you 0 in terms of the charge. But again, has no effect on the actual name of that particular compound. Any questions on that there? Down here, we have barium, which is a metal, and we have our friend there, hydrogen, which is actually a non-metal. And this is a situation where hydrogen comes after a metal. And that means that actually in this case, our barium is group 2, which has a +2 charge. And this is actually going to be the negative version of hydrogen. And in this case, we have 2 of them to balance out the +2 charge that's present. So we still name it based off of the barium. This would be barium, and hydrogen now it becomes the hydride, in this case, IDE. Any questions on any of those names there? All right, so when you do have the formula, you sort of want to approach it the same way. You want to kind of figure out what you're dealing with so you know how you should maybe put it together. So when we look at sodium oxide, sodium being a metal there, oxygen being a non-metal, so that definitely is ionic, which means we should have ions. So you really just want the basic ions for each of these guys and then put them together so that you equals 0 charge. So sodium, which is group number 1, means that it is Na+. Oxygen is group number 6, which means it is -2. So in this particular case, when we put it together, we actually need more of the sodium to balance it out. We need a grand total of 2 of them. And that means that our formula should be Na2O in this case. 2 sodiums, each at +1 gives us a +2. 1 oxygen there, or oxide at -2. So everybody balances out. Same thing here. If we look at silver nitrate, silver nitride. Silver nitride, silver is a metal. Nitride is nitrogen, which is a non-metal. So once again, it's ionic. Silver, again, being a transition metal, but it is one of those 3 that has a fixed charge. So we do know silver here has a +1 charge. Nitride, which is nitrogen, group 5 on the periodic table, has a -3 charge. So once again here, to put this together, we need to get it to 0. So we actually need not 1 silver, not 2 silvers, but we really need 3 silvers there to balance it out. And if you count them up, that's 3 silvers. So Ag3 and just 1 nitrogen will do it there. Any questions on that one there? Lastly here, magnesium, which is group number 2 in a metal. Chloride is a non-metal. So magnesium, the cation is magnesium with a +2 charge. The chloride is group 7, which means it has a -1 charge. And in this case, to get us to 0, we actually need 1 more of the chlorides. And that gives us a -2 for that and a +2 for the other. And putting that together gives us MgCl2. Any questions on writing the formulas? Now, I will say sometimes people are taught to do this move with the charges and the numbers and move them up and down. And you could do that and you just do it blindly. You will get a lot wrong because it doesn't work in all situations. So much better to think about it in terms of balancing out the charge rather than just randomly moving things. There's a number of situations where it will not get you the right sort of formula. If you're good with like 90% of the time, then you should just blindly do it. But other than that, you should think about it as balancing it out so you do get the right formula. Any questions on type 1 compounds? All right, then let us talk about type 2 compounds, which are also ionic. And once again, because they are ionic, it will have a metal and a non-metal. And much like before, our metal will lose electrons and become our cations. Our non-metal will obviously gain the electrons and become an anion. Just like previously, it is once again the metal that is the most important thing here. So the metal is the most important. And when we look at our metal, it will be a transition metal. Are just to the right of it on the periodic table under the staircase. Like lead, tin, etc., those guys, and that sort of area. Now in that area there, they have, and what they all really do have in common is they can create a variable positive charge. So these metals, unlike the previous type 1 metals, can have a variable positive charge. So really naming is all about telling people what you are dealing with. And in this particular case, what that means is you need to actually tell them in the name. The good news is it's pretty much named exactly like how you name type 1 compounds. The only additional thing is you need to do something with the charge. So the way that we go to name this is we do use the whole name of the metal just like previously. So we'll use our whole name of the metal. We will still use our non-metal with the IDE at the end. The only difference is in the middle, after the metal name, we do use a Roman numeral. And it's really important to remember that the Roman numeral is not how many metals you have. It is actually the positive charge on a metal if you took it out. So the Roman numeral is if you took one of those positively charged guys out, what the positive charge is. So that Roman numeral is the positive charge on the metal. We just took one out. So it's very common. People think that's how many metals there are and stuff like that, but it is that. So the reason we need to do things like that is, for example, if we had something like FeCl2. In this case, when we look at it, we see iron, which is a metal. We see Cl, which is a non-metal. And we see that iron is the most important thing. It is right dead center there in the transition metal region, which tells us it's a type 2 compound. It tells us that iron could have multiple types of charges. So the good news is you will always know what the charge is on what the metal is attached to. So in this case, it's attached to Cl, which is group number 7. And we know that it is a -1 charge for group 7. There's not just one of them, though. There are 2 of them, which means overall here we are sporting a -2 charge. And since this is an ionic compound, we still need to equal 0 when it's said and done. And we only have 1 iron to do that. So the charge here has to be +2 there to balance it out. That means that this name would be iron Roman numeral 2 because of the charge. And the last part would still be chloride. Doesn't matter that there's more than one of them. Again, no prefixes here. The reason we do this is because if we had something like FeCl3, this means that we still have the iron, but now we have 1, 2, and 3 chlorides, which gives us a -3 charge. And in this particular case, the iron would be sporting a +3 charge to balance it out. And this guy would be iron Roman numeral 3 chloride. Once again, the 3 for the charge on the metal. So because the metals can have a variable type of charge, you need to tell people, hey, in this case, we're dealing with the one with a +2 charge. In this case, we're dealing with the one with a +3 charge. You do not need to do that on type 1 compounds because they have fixed charges. So everybody knows sodium can only be +1. It'll never be anything else. So you don't have to tell people, hey, it's +1. That also goes for type 1 guys, as we talked about for the zinc, cadmium, and silver. Again, although they are transition metals, that is why we don't need to actually tell people what they are, because they only can make one type of charge. Here are some examples of some of the variable charges, like copper could be +2, +1, iron +2, +3. And then some of these guys outside, as I talked about, sort of in this region, again, although they are not transition metals, things like tin, which is Sn, and lead could have variable types of positive charge. So underneath that staircase to the right of the transition metals, you do typically need to also include a Roman numeral. Our good friend Mercury sometimes gives people a hard time, and Mercury looks something like this. So clearly, because it makes sense, the mercury there that has all the 2s is mercury 1. So that's mercury Roman numeral 1. And that's because it actually comes with the dimers 2 1s together. So it's actually, that's why there's the 2 on the bottom there, because it's actually 2 of those guys together. Each has +1 charge, gives you a +2 overall. The mercury with less 2s in it is actually mercury Roman numeral 2. So that's one that sometimes gives people trouble. How do you know if it's 1 versus 2? It's actually that bottom 2. It still stays in the actual formula a lot of times. So you'll still see it sort of show up. So if you had something like Hg2O versus HgO, top one is mercury 1 oxide because of that 2. Bottom one is mercury 2 because there is no 2. So that extra 2 sort of hangs around, and that's how you could sort of identify it as being mercury 1 or mercury 2. Any questions on that there? Now this got all messed up, but I think on your page it looks all right. But there are some older school ways of naming sort of type 2 compound or metals where we do not use Roman numerals. Use like ferric or ferrous for iron, cupric or cuprous for copper. They typically will end in one of 2 ways, either ic or ous, and they will not use Roman numerals. And they also will use more of the historical sort of name for those elements rather than iron or copper and stuff like that. And the ic, just for your reference, usually is the higher positive charge guy. And the one that ends in ous is usually the lower positive charge. For us, we will strictly use the Roman numerals. We won't use the old names. I will say with copper and iron, sometimes people still kind of use the older sort of version of the names rather than the copper 1 and copper 2 or iron 1 and iron 2. But for us in here, we'll strictly use the Roman numerals, not the kind of the older school name. And I apologize about how it all got shifted, but I think it looks much better on your handout, I think, than on that. All right, let's take a look at some then for each of these here. Why don't you give the names, and why don't you give the formulas for some of these here. So let's go with we'll go with iron 2 phosphide, should do PbO2. Let's do 10 4 sulfide. We have 3 chloride. All right, names on the left there, formulas on the right. Yeah, let's take a look, see how you're doing. We'll start here with the first one. We got CO, which is cobalt. That is a metal. It's a transition metal right next to iron. We got Cl, which is chlorine, which is a non-metal. So first off, we have a metal and a non-metal, which tells us it's ionic. We want to always focus on the metal. So the metal is a transition metal, which tells us it's type 2, which means we do need to sort of figure out the charge on it. Here we do have only 1 cobalt. We do know that chlorine there, or chloride, is group 7 and it's -1, and there are 3 of them, which means here +3 would be our charge there on the cobalt to balance it out. That means we use the whole name here of our metal, which is cobalt. We use a Roman numeral, which is 3 because of the charge on the cobalt. And we do chloride there. And again, does not matter that there is obviously more than 1 present. Any questions on that name there? Coming down here to the next one, we got Cu, which is copper, and we got I, which is iodine, which is a non-metal. So again, ionic, and the copper dictates that we do need to figure out the charge. In this case, the iodide is group 7, which has a -1 charge. That means our cation here is copper with a +1 charge. And that would mean that we would use the whole name, which is copper Roman numeral 1 again for the charge on it, and we get the IDE ending there for our iodine. Yeah. Coming down here, we got SN, which is tin, which is a metal, Br, which is bromine, which is a non-metal. So it's ionic. Tin, again, is not a transition metal, but it is just to the right of it, and it does fall under the same sort of naming. Like we talked about, it can have multiple types of charges. In this case, we only have one tin, but we do have 4 of these BRs, which are each group 7, which means it has a grand total of -4. So in this case here, our tin would be a +4 charge. And that means that the name here would be tin Roman numeral 4 because of the charge. And once again, although we do have a variety of bromines there, it is just going to be bromide at the end. Yeah. Any question on those 3 there? Coming to the last one here, our PbO2. That is lead, which is a metal. That is oxygen, which is a non-metal. And again, it's ionic. Lead, just like tin, outside the transition metal region, but still going to be named the same way because it can have a variable type of charge. We have, in this case, only 1 of the leads. We have 2 of the oxygens. Each are group 2, which means it's actually -4 here. That means the lead is +4, not 2 if you did your switcheroo in a place where you would get wrong answer in this case. Yes, if you just kind of did that move. This would be lead, Roman numeral 4, oxide. So again, cautionary note, switcheroo doesn't work every situation. Yes. So that is lead, Roman numeral 4, oxide, not lead 2 oxide. Yeah. Any questions on any of those names there? All right, so now we're going to write the formulas on the other side. Nice thing about this is it pretty much tells you everything. So iron Roman numeral 2 means that I have an iron with a +2 charge is pretty much what that means. Phosphide is phosphorus on the periodic table, and that is group 5, which means it has a -3 charge. When we put that together, simplest number to get it to 0 is 6. You get that by just multiplying the 2 numbers together. 3 times 2 is 6. That means to get iron to 6, we need a grand total of 3 of them, right? And to get the phosphorus there to 6, we need 2. So that's what we should write. Iron, there are 3 of them, and phosphorus, there are 2 of them. And that would be our formula there. Looking at the next one, which is tin Roman numeral 4, tin being SN. The +4 comes from the Roman numeral. The sulfide, which is sulfur from the periodic table, which is group 6, has a -2 charge. Common number there is actually 4, right? So we actually need more of the sulfide here. We actually need 2 of them to get to -4 to balance out the +4. And that means we end up with 1 tin and 2 of the sulfurs there. Yeah. Any questions on those 2? Lastly, here we have chromium, Roman numeral 3. So chromium is Cr +3 because of the Roman numeral. And chloride is group 7, which means it has a -1 charge. So in this case, to get us to 0, we actually need more of the chloride. And we do need a grand total of 3 of them to get us to -3 to balance out the +3 that we see here. So that would give us CrCl3 in this case. Yeah. Any questions on any of those? Clearly, you need to do both ways. Yes, the name and the formulas. Yes. Okay. So these are type 2, which are ionic. The next thing we're going to talk about does sort of follow the same sort of, and this is a decision tree like you have, follows the same sort of rules really in most cases as ionic compounds. And these are polyatomic ions. And polyatomic ions are groups of nonmetals that are together that have a fixed sort of charge. So for example, if we looked at something like NH4NO3, this is actually 2 polyatomic ions together. This guy over here is NH4 plus. The 1 nitrogen, the 4 hydrogens all stay together, has a +1 overall charge. This guy over here is NO3 minus. The 1 nitrogen and the 3 oxygens also all have a -1 charge overall. That is why when we put it together, it is 2 ions. And basically +1, -1, we just need one of each of them to get there. These are things that are covalently bonded together. They are sharing electrons. In fact, I think we drew both of these in the previous chapter when we drew our Lewis structures. This is NH4 plus. They are sharing electrons because of the way sharing and the sharing that occurs. It actually ends up with an overall positive charge. Nitrate here looks something like this. So these are things that share electrons, but do have charges. And that's why they never break apart into like all the individual elements. Yeah, because they're sharing those electrons. So they do move around as units. So this entire unit moves around, this entire unit moves around. They just don't break apart into alphabet soup and everybody falls apart. Again, that's why ultimately what we're doing is just putting together basically a positive guy and a negative guy. Works the same way really as a traditional ionic compound like type 1 and type 2, which means positive guy first, negative guy second. They also do have special names. So NH4 plus is the ammonium ion. NO3 minus is the nitrate ion. And really the good news about polyatomic ions is you pretty much just use their names. So when we would put it together here, NH4, NO3, that is ammonium nitrate, ATE. Now, I would say that, as we will see here in a second, pretty much the majority of all polyatomic ions are usually negative. So there are a few kind of positive guys, ammonium, which by the way should not be confused with ammonia that we will see later. Ammonium is one of the few sort of positive guys that you'll come across. So in most cases, what happens is our polyatomic ions are usually hooked up with a metal. And a lot of times what you end up getting is a metal and a polyatomic ion. And that sort of rule that we talked about earlier, that the metal is the most important thing, it is still the most important thing with a polyatomic ion. And you would follow basically type 1 or type 2 rules, which means if the metal has a fixed charge, you don't need a Roman numeral. So you would just use the whole name of the metal and the polyatomic ion's name. And if the metal is a type 2 metal, you would need the metal, Roman numeral, polyatomic ion name. So most of the time, that is pretty much how you would probably name most of these polyatomic ions. Again, if it's type 1, you just use the metal and the polyatomic ion name. If it is a type 2 metal, you use your metal, your Roman numeral, and then the polyatomic ion name. So I would say probably 99 times out of 100, that's probably how you're going to sort of interact with a polyatomic ion. It will interact really with a metal. Any questions on that there? So here's a list of polyatomic ions, and they are things, and kind of weird spacing on my slide here, but I think it's better in your book and stuff, and also in your notes. But there are things that you do need to know, which is, frankly, you need to know the names and the charges that go with them. You do need to know the charges because, frankly, you got to put it together, right? It's an ionic compound, so you got to put it together to balance 0, and you do need to know the names. There are ways that you could kind of remember some of these or help yourself remember some of these. So, for example, if we looked at something like NO3 minus, that is nitrate. NO2 minus is nitrite. If we look at SO4 2 minus, that is sulfate. And if we look at SO3 2 minus, that is sulfite. Now, in a group of 2, and basically the only difference between these 2 guys is the number of oxygens. Yeah, the charge is the same in both. They both have a -1 charge. The only difference really between these two things is the number of oxygens. They both have a -2 charge. So in a group of two, the one that has the most oxygen typically will end in ATE. So that's why it's nitrate. The one with the least number of oxygens will end in ITE. So that's why the guy on the bottom there is nitrite. So usually more oxygens will end in 8. Less oxygens will end in ITE. So that's a really good way to sort of remember these. You could remember, for example, all the 8s and know that the ites are just 1 oxygen less, right? Or vice versa. You can do all the ites and know that if you needed an 8, it's just 1 more oxygen that you would put in there. So that's a good way to do it. There are also some that are a group of 4, like ClO4 minus, ClO2 minus, I'm sorry, I could count, right? 3 minus, there you go, 2 minus, and ClO minus. That gives us 4. That looks better. These are all related to each other. The only difference in each of them is the number of oxygens. They all have a -1 charge. So in a group of 4, you can kind of do the same thing. You can break it apart by lowest oxygens and most oxygens. And clearly the lowest oxygens on the right here should end in ITE. So this would be chlorite. This would be chlorite as well, but clearly cannot have the same name for 2 different things. So in a group of 4, the one with the least number of oxygens also will start with hypo. So that is hypochlorite, that is chlorite. If you go to the left there, those are the guys that have the most oxygen. So they'll end in 8. This will be chlorate. This guy would also be chlorate, except obviously you can't have 2 of the same name. So the one with the most oxygens will start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite. That's a halogen, which means, frankly, you can swap out that guy for any halogen and it's named the same way. So if I had something like BrO3 minus, instead of chlorite, instead of chlorate, that would be bromate. Yeah. So, that is how you can swap those guys out. Also, if you have something that is kind of like a group of 4, but you're not sure it's a group of 4, but you go like, hey, there's like MnO4 minus, that is permanganate. Which means that if I had MnO3 minus, that would be manganate. If I had MnO2 minus, that would be manganite. And if I had MnO minus, that would be hypomanganite. So you could actually turn those into your kind of group of 4 by just kind of using those before and after sort of parts of the name. Now, not all of them end in ITE or ATE. There are some that end in IDE, so like hydroxide, IDE, azide, cyanide, those guys end in IDE, but a vast majority of polyatomic ions will end in either ATE or ITE. And as you can see on this list, for the most part, that ammonium, which looks like the 4 got way out of place there, is NH4 plus, is really one of the few sort of positive guys that you come across. Hydronium ionic you do come across as well, but not usually in naming. So in acid basis you do, but really they will be hooked up with those metals. Any questions on that so far?